So now we can apply these trigonometric substitution techniques we just learned to a full integration problem. And as I mentioned before, there is just one piece we're missing when we start looking at this as integration that we'll have to include. Otherwise, we've done most of the difficult work with the triangles. So if we were asked to integrate let's just say 5 over the square root of 16 minus x squared dx. Because I see that difference of squares in there, and I know u substitution is not going to work because my u would be 16 minus x squared, my du would still have an x in it, but I don't have any other x's in this problem to get rid of. So once you look at the problem and you recognize that u substitution is not going to work, if you see a sum or difference of squares, you can try trigonometric substitution. So we had said earlier that if it's a difference of squares, the first piece is hypotenuse squared, the second piece is leg squared, and it will usually work out better if you write that on the opposite side. So I'm going to draw my triangle. It's very important that you draw this triangle. It might not have seemed as important when we were just doing some simplifications, but with the integration, it's definitely going to be very important to draw your triangle because you're going to have to refer back to it at the end in order to get the trig back out of your problem and replace it back with x's. So our hypotenuse is going to be 4, and my opposite leg is going to be x, and according to the Pythagorean identity, that would make this adjacent leg the square root of 16 minus x squared. And we want to set up a trig function that avoids the difficult side. So we're just using opposite and hypotenuse, which is sine. Sine of theta is the opposite side divided by the hypotenuse. And if we solve that for x, we get 4 sine theta. Now when I do this substitution for the x, I am no longer going to have that x in my integrand. It's now going to be a function of theta, which means I also need to replace this dx as something in terms of theta. So all we have to do to figure out what to do to replace the dx is just take the derivative of both sides of this substitution we've decided to do. So if x is 4 sine theta, the derivative dx is 4 cosine theta, d theta. So that's the one piece that we were missing earlier when we were only doing substitutions. Now that it's in the form of an integral, we also have to replace the dx, because we are not going to see any more x's in this entire problem. We're just going to see thetas, and we're going to want to integrate with respect to theta. So now we're going to use these two equations to rewrite our integral. Anywhere you see an x, you're going to put 4 sine theta, and then instead of dx, we're going to put 4 cosine theta d theta. So the 5 in the top is perfectly fine, and then that's divided by the square root of 16 minus your x squared. So 4 sine theta squared. And then instead of dx, I'm putting 4 cosine theta d theta. And I want to simplify this as much as possible. The first thing I'm going to do is I'm going to go ahead and multiply them together. So my numerator is 20 cosine theta. And remember, your sum or difference of squares is always going to simplify with a Pythagorean identity. Once we square that 4 sine theta, we'll see that those two terms inside the square root have a 16 in common. And if we factor the 16 out of both of them, then we'll actually be able to see our Pythagorean identity, 1 minus sine squared theta. We can't cancel that square root while there's still addition or subtraction underneath it. So 1 minus sine squared theta is equivalent to cosine squared theta. And now I've eliminated any addition or subtraction under my square root, and I can just take the square root of each piece. So this is 20 cosine theta over 4 cosine theta. And that's going to simplify really nicely because the cosines are going to cancel, and 20 divided by 4 is just 5. So all we're being asked to integrate here is 5 with respect to theta. So just think of that like we would if it were an x. Anytime you integrate a constant, you just throw your variable on it. But that is not our final answer. That theta is completely arbitrary and made up by us to make the problem easier. So once you finally do your integration, you're going to have to refer back to your triangle to figure out how to get this back in terms of x. Now, there is no trig function in our answer. It's just a theta. So whenever you have a theta all by itself with no associated trig function, you're going to use inverse trigonometry. I need to know what to replace theta with. So I'm going to refer you back to the original substitution we did. We said that x was going to equal 4 sine theta. We're going to solve this equation for theta. So I'm going to divide the 4 over. And now I've got sine theta equals x over 4. And now to get the theta out of the sine, we do inverse sine or arc sine. So theta is sine inverse of x over 4. And then I can plug that in right there. So my final answer back in terms of x is 5 sine inverse of x over 4. Now there's actually a formula for this, and I've referred to that formula in other sections, but I have tried to emphasize to you that you do not have to memorize those antiderivatives that involve inverse trigonometry. We just did this whole problem and got an inverse trig answer without ever looking at one of those formulas or memorizing one of those inverse trig derivative antiderivative formulas. So that's why I really don't think it's important that you have to memorize those. Let's look at another one, because typically the thetas in your answer will have a trig function attached to them, and we need to talk about what to do with those. So this time, let's try to find the antiderivative for x squared over the square root of x squared plus 4. Anytime you're asked to do an integration problem, you should always just check to see if a simple u substitution is going to work. And it's not in this case because your two instances where you have an x are both squares. They're the same power. We need the one inside the composite function to be 1 degree larger than the one outside in order for u substitution to work. If I were to let u equal x squared plus 4, du would be 2x dx, a linear x, 1 power smaller. So that would not cancel off my numerator completely because I have an x squared in my numerator. So then your next option, if you know u substitution is not going to work, you can say, oh, well, I've got a sum of squares here. I can set up a triangle that has a similar pattern and just use trigonometry to do this. Now remember, if it's a sum of squares, if you match it back up with your Pythagorean theorem, these both have to be legs. And the substitution and the integration are going to work out nicer if we put the variable on the opposite side. And then our other piece is 4, but that's the square of our other leg. So our other leg is actually going to be 2. And you can check your Pythagorean identity that has legs of x and 2, and your hypotenuse will end up being the square root of x squared plus 4. We want to use the easy sides, which are the opposite and the adjacent. We want to avoid that difficult side that has the square root. So I'm just going to use opposite and adjacent, and you need to think about what trigonometric function uses opposite and adjacent, and it's tangent. So tangent of theta is opposite over adjacent. And if we solve that equation for x, we will have our correct substitution. X needs to be equal to 2 tan theta in order for that sum of squares to simplify nicely with a Pythagorean identity. We also are going to have to replace dx. So we're going to take the derivative of this as well. And the derivative for tangent is secant squared. Now we're going to take both of these and plug them back into our integral to try to get our integral completely written in terms of trigonometry and then simplify it as much as possible. So in my numerator, it says we need to have x squared. So take your x substitution of 2 tan theta and square it. In the denominator, we have the square root of x squared plus 4. And then off to the side, we have our dx, which we just figured out to be 2 secant squared theta, d theta. If you're not sure to start with our simplifying, always start with the sum or difference of squares. That will always simplify. And then you can, once you get rid of that piece, it'll look a lot nicer once that square root is gone. So that's where I'm going to start. I'm going to kind of ignore everything else. Well, no, I'm going to go ahead and put that in my numerator. So this is, let me work out my squares. This is 4 tan squared theta over the square root of 4 tan squared theta plus 4 times 2 secant squared theta d theta. And I'm going to go ahead and put it in my numerator, and I really have 8 tan squared secant squared in my numerator. In my denominator, we've got 2 separate terms under the square root, so it's going to be tempting. You're going to say, everything under there is a perfect square. I'm just going to go ahead and square root everything. You cannot do that at this point because of the addition. We have to use a Pythagorean identity to get rid of the addition first. So go ahead and factor the 4 out that both of those terms have in common. And if we do, we're left with tan squared plus 1. And there is our Pythagorean identity. Tan squared plus 1 is equal to secant squared. And now that the addition is gone, we can just take the square root of each piece under our square root. Which is 2 secant theta, d theta. And we've got some things that can cancel here. I've got a secant in the bottom, and I've got some in the top. And then between the 2 and the 8, I can simplify that to just a 4. And now what we have is 4 tan squared theta secant theta, d theta. Now it's just a trig integral like we calculated in section 3. So we need to remember how we calculated all those trig integrals in section 3. With tangents and secants, we need to try to figure out which derivative we can hold on to. And in that process, based on which derivative we're holding on to, we want to get everything else in that integral written as the the corresponding function that will create that derivative. Now this one is kind of a unique case because our two options are to either hold on to a secant squared, which we don't have. There's no secant squared to hold on to. Or hold on to a secant tangent. If we hold on to a secant tangent, we're doing that because our ultimate goal is to do a u substitution for secant. So if I were to try to hold on to a secant and a tangent, what I would have left over from my original integral is just another tangent. And it is not possible for us to hold on to secant tangent and get everything else in the problem written in terms of secant. The only way we switch back and forth between these trig functions is with the Pythagorean identities, which will switch out squares for us. And the tangent that we have left, it does not have a square. So this one's actually tricky. I know that this is not going to work, so I'm going to explore this option. We don't currently have a secant squared in there, but I could get a secant squared in there if I go ahead and replace tan squared right now. Replace the entire tan squared. So tan squared is equivalent to secant squared minus 1. And if we distribute that, that is secant cubed minus secant. We're going to think of this as two different integration problems because we're going to integrate both of them very differently. For the first term, I'm actually going to use integration by parts. We didn't ever get a chance to look at an integration by parts problem that involved a u equaling a trig. We had the one really weird case where we had exponential and trig, but this one's going to work out differently. So the antiderivative for secant is easy. As we said back in our section 3 video, we've got a table in the book that gives us all the antiderivatives for secant, tangent, secant, and cotangent, and they all involve logs. So that one's going to be pretty easy to do. But this one is where we're going to have to do the most work. So I'm going to write this actually as secant squared times secant. And I'm going to do integration by parts. And the reason I'm going to do integration by parts on this is because one of those functions is very easy to find the derivative for, and the other one is very easy to find the antiderivative for. And while staying with nice simple trig functions. With this case, we're going to want to let u equal secant because it's very easy to find the derivative for secant. And I'm going to let dv equals secant squared theta d theta because it's very easy to find the antiderivative of secant squared. In order to set up our integration by parts formula, we need to find du and v. So the derivative of secant is secant tangent. And the antiderivative of secant squared is just tangent. And remember, our integration by parts formula is uv minus the integral of v du. So I'm going to try to set this back up again. And don't forget about this guy that we pulled off to the side. He's not an issue right now. He's going to be easy to integrate. So I'm just worrying about my secant cubed for right now. So if I do u times v, I get secant theta tangent theta minus the integral of v du. That's going to be secant theta tan squared theta. And then we also have this minus 4 integral of secant theta. So I've got 4 secant theta tangent theta minus 4 times the integral of secant theta tangent squared theta d theta minus 4 times the integral of secant theta. Now, the secant theta tangent squared theta, this is actually what the integral started off as when we first switched it all over to trigonometry, remember? Right here, tan squared theta secant theta. So that's what all of this is equal to. All of the simplifying I've done is to figure out what the integral of 4 tan squared theta secant theta simplified down to. And this is what it has simplified down to at this point. This is very similar to the problem we saw with the exponentials and the trigonometric functions in integration by parts, where once you're able to get yourself back to where you started, you set it equal to what you started with, and then group them together. So I'm going to take this minus 4 secant theta tangent squared theta and add it over to the other side. And it's going to cancel away here, and then we're going to get that 8 times the integral of tan squared theta secant theta equals 4 secant theta tangent theta. I'm going to go ahead and do this integral while I'm at it. I've got minus 4 natural log of secant theta plus tangent theta. And again, that is from a table in our textbook. Now this is not our answer, because what we were originally trying to figure out was what the integral of 4 tan squared secant is. I've got the answer for 8 tan squared secant, so that's double what I want my answer to be. I want to know what just 4 of them is. It's telling me what 8 of them is equal to. So I need to go ahead and divide everything by 2. And then it will give me an answer for what 4 tan squared secant theta is. It is 2 secant theta tangent theta minus 2 natural log absolute value secant theta plus tangent theta. This is not our final answer. I know we've done a lot of work to this point, but there is one more step. We put the thetas into this problem. When this problem was given to us, it started off with x's, remember? And we put the thetas in it to make it easier. So now we've got to look back at our triangle to help us figure out how to get the thetas back into the x's. So our answer here has secant theta and tangent theta. All you have to do is look on your triangle and see what secant theta is equal to. So secant is hypotenuse over adjacent. So secant is the square root of x squared plus 4 over 2. And then we need to know what tangent is. Tangent is opposite over adjacent. So we need to look back at our triangle. Opposite is x, adjacent is 2. So tan theta can get replaced with x over 2. And we can do a little bit of simplifying there in that first term and have the 2's cancel. And if you want to avoid having your variables inside a fraction, we can pull that remaining 2 out front as just a 1/2 coefficient. So it's 1/2 x square root x squared plus 4 minus 2 times the natural log of the absolute value of x squared plus 4 all over 2 plus x over 2. This is a very tricky problem because it requires us to put together a lot of things that we've learned so far in Chapter 7. We have to first know how to do the substitutions that we're learning in Section 4. Once we do those substitutions, we have to know how to do the trigonometric integration, which we learned in Section 3. One of those trigonometric integrations required integration by parts, which was in Section 2. So this is a very tricky example that requires us to pull from pretty much everything we've learned so far in Chapter 7. I do want to look at one more, if you're not already exhausted after that one. We have done one that turns out to be just a regular old theta, and we said if you have a theta in your answer, it's always going to turn into some inverse trigonometry. Just refer back to your original substitution and solve for theta. And then we did one, that one had a difference of squares, and then we did one that had a sum of squares. There is another type of problem that we might see that requires us to use our power reducing formula. And when you get to your final answer, you might be confused as to how to rewrite these answers from theta back into x. So I want to make sure to show you one of these. So for the last example, we're going to try to find the antiderivative for 3 over 4 plus x squared, that quantity squared, with respect to x. The first two examples had square roots in them. A square root is not a requirement for these problems. The only requirement is that we see a sum or difference of squares, which we do here. Now, foiling out that denominator is not going to be helpful at all. We would prefer to leave it as a sum of squares. That way we can apply our trig substitution method. So once you find your sum or difference of squares, remember how these guys are set up. If it's a sum, those are our legs. And I will transfer those legs over to a triangle. This triangle is really important because we're going to have to reference this triangle when we're done and we want to get it back in terms of x. Now with the sum of squares, we did say it would be easier if the variable is on the opposite side. And then I'm going to put my one that has a value on the adjacent side. That means my hypotenuse would come out to be the square root of 4 plus x squared. Now that doesn't match what I have in my integral, and that's perfectly fine. As I told you earlier, that's not always going to be the case. So don't always expect the square root piece to be in your problem. We do want to avoid the square root piece because that one is difficult. Trying to integrate that piece would be really tricky. What we want to do instead is use those nice easy sides, which we have put at the opposite and the adjacent position. So opposite and adjacent is tangent. Tangent of theta is opposite over adjacent. So our substitution is x equals 2 tan theta. And then remember, we also have to replace dx. The derivative for tangent is secant squared. So we could use these two pieces to rewrite our integral. So I've got 3 divided by 4 plus my x, which is 2 tan theta, squared, all squared, times my dx, which we just found was 2 secant squared theta, d theta. So I've done nothing but direct replacement at this point. I replaced the x with 2 tan theta, I replaced the dx with 2 secant squared theta. I'm going to go ahead and distribute my tangent here. There's no addition or subtraction inside those inner parentheses, so we can go ahead and distribute that. And I'm going to go ahead and put this guy in my numerator. So I've got 6 secant squared theta over 4 plus 4 tan squared theta, all squared, d theta. Now, the expression inside of the square, we're going to be able to simplify that with a Pythagorean identity. If we pull that 4 out of both of them, we're going to have 1 plus tan squared. And 1 plus tan squared is equal to secant squared. Now squaring that expression in the bottom is much easier. Now that we've gotten rid of the addition, we can just distribute the square to each piece. So now I've got 6 secant squared theta over 16 secant to the 4th theta. And a bunch of those secants will cancel. We can also reduce our coefficients. They're at least both even numbers. We can pull a 2 out of each of them, and I'll get 3/8. And I'm just going to move it to the front of my integral because we really don't have to do anything with that until the very end. Now my secant squared is left in the denominator. And it would be a lot easier to work with if we pulled that to the numerator as a cosine squared. And now we're back to section 7.3 material, where we just have to do a trig integral. And remember, with sines and cosines, if we do not have an odd power to work with, we want to use our power reducing formula. Cosine squared is equivalent to 1 plus cosine of 2 theta all over 2. And I'm just going to pull that 2 out in the front with my 8 and call it 3/16. And now we've got something we can integrate. The antiderivative of 1 with respect to theta is theta. The antiderivative for cosine is sine of the exact same angle. And remember, you have to flip that coefficient from the angle in the front. So we've got 3/16 theta plus 3/32 sine of 2 theta plus c. So I've got that bare theta again. It doesn't have a trig function attached to it. In those cases, we go back to the original substitution we did. We said that tan theta is x over 2. Well, if tan theta is x over 2, that means theta is tan inverse of x over 2. Let's see if I can go a little slower. That's good enough. So remember, we originally said tan theta is x over 2. And to isolate the theta there, we're going to have to do tan inverse. So that's going to be the replacement for the first piece. For the second piece, though, you can't go to your triangle because this second piece is referencing a triangle that has the angle 2 theta inside of it. And if you look back at our triangle, it does not have 2 theta inside of it. It has just regular theta. So we need to use a trig identity to rewrite sine 2 theta in terms of something equivalent that uses just regular theta. So we have to use our double angle formula to fix that piece. So now I've got 3/16 tan inverse of x over 2. That piece is done and ready to go. That's half of our answer. But for the second piece, we're going to have to replace sine 2 theta with its double angle identity, which is 2 sine theta cosine theta. Now I can refer to my triangle because now I've got trig functions that reference the angle theta in them. So I've got 3/16 tan inverse of x over 2. 2 times 3/32 is going to be 3/16. And then we've got to look at our triangle to figure out what sine theta and cosine theta are. So let's go back up to our triangle here. Sine theta is going to be opposite over hypotenuse, so x over the square root of 4 plus x squared. Cosine is adjacent over hypotenuse, so 2 over the square root of 4 plus x squared. And then we'll just try to simplify down that last term really quick for our final answer. So 3/16 tan inverse of x over 2. And then this 2 can cancel here. We've got 3/8. Square root times a square root is going to just leave the radicand. So I've got 3x over 8 times 4 plus x squared in the bottom. Most of the problems work out pretty straightforward, where your antiderivative is just going to have a trig function, and you can look back at your triangle to figure out how to replace the trig function. But I wanted to make sure to show you this 2 special cases here, and that's when we have just a theta all by itself in our answer. And we saw in the last 2 examples that we're going to end up using inverse trig to fix that. We're going to use the original substitution. To solve for theta, and it will always end up being inverse trigonometry. The other kind of strange case that we see was when we've got 2 theta as an angle. The triangle we set up does not have an angle of 2 theta labeled. We cannot use our triangle from the beginning of the problem to simplify trig functions that have an angle of 2 theta. What we have to use is one of our double angle identities to rewrite this. In terms of just single theta, and then we can use our triangle to finish out the rest. So these are just 2 special cases that we see after we do our antiderivative, and this is how we are going to deal with them when it's time to change all of the thetas in the trigonometry back into x's. All of the other antiderivatives we get should involve just a trig function of theta, and we can reference different sides of our triangle. So like tangent of theta is opposite over adjacent, so tangent can be replaced with the opposite side divided by the adjacent side. So everything else should have trig in it. But these are the 2 special cases we see: a theta all by itself, or a trig function that has 2 theta. So a theta all by itself is going to turn into inverse trig, and a trig function with 2 theta, we're going to have to use a double angle identity to get it rewritten first. Once it's in terms of theta, then we can reference our original triangle.